Hi, everyone. Thanks for joining us on our presentation for our final project for the Robotics Fundamentals class at University of North Dakota, the fall semester of 2025. Our project is on object detection-based robotic pick and place arm, and it will be by my teammate Sajid Kapali.
Hello.
And myself, Bayo Rov-Ikpah. Next slide.
You can click.
Okay.
Just click anywhere.
Yeah, it wouldn't advance. Okay, so the project concept, a camera monitors the conveyor and captures real-time images. A computer vision system analyzes the images and identifies when an object reaches a predefined pickup location. Upon detection, a controller triggers the robotic arm to perform the pick and place operation. The robotic arm moves the object to a designated location, such as a packing box. So on the right, we can see the setup with the conveyor belt and the robotic arm moving things around. Next slide. Robotic arm overview. So all the joints are Revolut joints, by the way. We have the base joint, which rotates the arm horizontally to align with the pickup and placement locations. The shoulder joint, which provides vertical lifting motion and sets the primary reach of the arm. The elbow joint, which extends or retracts the arm to reach objects at different distances. We have the wrist joint, which controls the final orientation of the end effector for accurate grasping. And then we have the gripper or the end effector, which is all the way on the right, is a servo actuated mechanism used to pick up and release objects. So the DH table for the Danovic-Hardenberg parameters, we have the theta I, which is the joint angle, which is the rotation from the xi minus 1 to the xi axis, measured about the zi axis. And then alpha I minus 1 is the link twist, is the rotation from the zi to the zi plus 1 axis, measured about the xi axis. And then we have the AI minus 1 is the link length, the distance from the ZI to the ZI plus 1 measured along XI axis, and the DI is the link offset. It's the distance from the XI minus 1 to the XI axis measured along the ZI axis. Next slide. So for this, I'll hand to Sajib.
Thanks, Bia. Am I muted?
No, I can hear you.
Yeah. Okay. So we can find the forward kinematics using this flowchart easily. We start with the DH table, then we compute all the individual transformations of the consecutive links T01 to T34 using the DH matrix Ti, which is this one. And then we multiply all the individual transformation matrices to get the final transformation from the base to the end effector T04. And from that matrix, we can extract the end effector position, which are Px, Py, and Pz. These are the coordinates. And we can also extract the end effector orientation Phi, which is the summation of angles theta 2, theta 3, and theta 4. About the end effector orientation, it can be also a design solution, like design requirement. If we want a certain end effector orientation, we define the phi and then we work backwards to figure out the angle values. Then inverse kinematics is exactly the opposite thing of for kinematics. Here we define a position for end effector, a desired position for end effector, and we work backwards to find out the joint angles. To find out the base joint angles, we can just project the joint and the end effector position on a horizontal plane, and it can easily be found by like chain and tan inverse py by px, where py and px, these are the coordinates of the end effector position. And then the problem becomes simply a three-link planar geometry, where this is the shoulder joint, this is the elbow joint, and this is the wrist joint. We first figure out the shoulder joint and the elbow joint theta 2 and theta 3, and then uh, we solve we find the value of theta 4 to get the desired end effector orientation. Here's the kinematics visualization. We used simply this set of values to find out where the end effector is, and that's the end effector position. And then we work backwards, like provided this end effector position here on the inverse kinematics and got two solutions actually, and one of them aligns with our forward kinematics orientation. Next is the simulation, and I'll hand it over to Beer to expand or describe.
Thank you, Sajib. So the simulation was done in MATLAB and Simulink. The robot model was developed using Simscape Toolbox, which is part of Simulink. So the overall environment is MATLAB, and then we go down to Simulink. In Simulink, we developed the robot model um, and also the forward kinematics, as well as the inverse kinematics that drive the robot. And the models were then run within MATLAB environment using the robotics toolbox for the actuation of the joints and end effector. Next slide. So in the robot model, as you can see in figure one, which is in the background, we have the world frame, and also we have a solver configuration and a mechanism configuration. And then we have a world to base transform that ties the base link and also the base to J1 that ties the joint one, and then a joint one to link one and so forth. So we do that in the forward direction all the way to the end effector. And then in figure two, we see that we create those links as subsystems and tie them to the joints. So you can see the base and link one through the end effector. And then in three, we include the inputs. So for the forward, this is trying to develop for the forward kinematics because we'll be providing the inputs and also measuring the outputs based on the inputs that we provided. And then we take all of this and also create a subsystem that we then call robot. Next slide. So in here we have the forward kinematics. So in MATLAB, we were able to run the DOF4 underscore ARM code to get this into the workspace. And then we take the measured values and put it to the get transform component of the forward kinematics. It takes that and then also that moves on to the coordinate transformation conversion. And then the homogeneous transformation takes us to the XYZ position of the end effector. So we have our signal generator or signal builder that we provide the angles that we want into the robot. And also we incorporate a scope that we can be able to view the behavior or just even the signals that we send. For the inverse kinematics portion, we have a scenario where we're feeding in the end effector location. So the end effector location, which is the XYZ position, into that block, the inverse kinematic block. And then we have some biases that we provide for initial, so weights, initial guess, and then that moves to drive the robot. It does some iterative process just to be able to get back to us uh, the angles that would get that robot to the XYZ position. Sadly, the The animation worked because the simulation we did using our desktop, my desktop, which has a GPU on it, at the time of our presentation, our laptops would not handle the 2025 MATLAB version with the WebGL, and we experienced some challenges, so we couldn't show you the animation. I would hand over to Sajid for the next slide.
Thanks, Beer. Uh, okay, so this is about system overview. We have a camera that provides a live feed to the object detection like algorithm, which is like built on Python and OpenCV. So after the object is detected, it sends a like command or signal over serial USB to the Arduino, and Arduino provides the control sequences to the servo board, servo controller, and the controller then sends the command to the 4D of robot arm, which performs the action pick, place, and home. And we can see a demonstration here. So this section, it's the Python GUI that monitors the status of the object, if it is in the right place or not. If it's not, it will show empty, and if it's in the right place, it will like show the status is ready or the status is stable, and send a signal or command to Arduino so that the robot arm can get activated. I will play the demonstration video here. It's kind of for better view. So I placed the object on the region of interest, and it says status is stable, it's a cube, and Arduino is ready and busy because it's going to pick up the object. I'll just speed up the video a little bit. So it picked up, and now it will place the object and then come back to the home position. And it is designed for specific cube-shaped objects so that it doesn't pick up any other object. So I placed a mouse here, and it shows the status is empty because there is no object. But if I place a cube again, it says a cube. Okay, and Arduino is ready. So ARM will go and pick up. We'll initiate the sequence, pick up, place, and go back to home. I'll just fast forward. Yep, that's it. For next slide, I'll hand over to Beer.
Thank you, Sajid. So we've been able to demonstrate that a robot is capable of picking up an object in a specified location and placing it in a specified other location, making sure that it is the object of desire. For future work, we plan to incorporate computer vision, and also this work can be developed in such a way that it could do more complicated tasks like color sorting, picking different objects and placing them at different locations. So that is it from both of us. Thank you so much for listening to our recording,
Thank
and
you,
have a
everyone.
good time.